I'll be walking through my high distinction task for SIT 202 Computer Networks and Communication. I've built a custom ping application in Python from scratch using the raw sockets and the ICMP protocol without using any built-in ping commands. I'll first walk through the code section by section and then demonstrate it running live. At the top of the file, I'm importing five built-in Python libraries: OS and SYS for system level operations, and socket for raw network connection, struct for packing and unpacking the binary data, select for timeout handling, and time for recording the timestamps. Then I have defined four constants: 0, ICMP type 8 for echo request, type 0 for echo reply, 1 second timeout, and a packet size of 56 data bytes, which is the same default the real ping utility uses. The first function is the calculate checksum. When we send a packet across a network, the receiving host needs to verify that the data was corrupted or wasn't corrupted while it was in transit. That's what the checksum is for. The function first paths the data to an even length if needed. Then it loops through the data 2 bytes at a time, combining each pair into a 16-bit number and then adding them all to a running total. The while loop at the end folds any overflow back into the 16 bits. Finally, it takes the ones complement, flipping all the bits to produce the final checksum value. This gets embedded into the packet header before sending. Then we have the build packet function. The packet function, it constructs the actual ICMP echo request packet. It starts by getting the current process ID masked to 16 bits, which will be used later to match our replies against our requests. It first builds a dummy header with the checksum field set to 0. This is required because the checksum is calculated over the full packet, including the header. The payload embeds the current timestamp using the struct with padding added to each to reach the full 56-byte packet size. Storing the timestamp in the payload means we can calculate a very accurate round trip time later. The checksum is then calculated over the dummy header plus the payload, and finally the real header is built with the correct checksum inserted. The complete packet is the header plus the payload, as it is returned data plus header. So then we have the sendPing function. The sendPing function is straightforward. It resolves the host name to an IP address using the socket.get host by name. It builds the packet and it sends using the raw sockets send to method sock.send to. It returns the destination IP so we can display it in the output later. Then we have the receive ping function. The receive ping function is the most detailed part here. It calculates a deadline, send time plus 1 second, and enters the loop. On each iteration, it checks how much time is remaining. If we are past the deadline, it returns none, which triggers the request timeout message. The select call waits on the socket for the remaining time. If it times out with no data, we again return none. When a packet does arrive, we record the receive time and read the raw data because the operating system prepends a 20-byte IP header to every received packet. The ICMP header starts at 21 byte. So I slice from position 20 to 28 and unpack the fields using the struct, extracting the type, the code, check some packet ID and the sequence number. I then check two things. First, that the ICMP type is 0, meaning it's an echo reply and not some other ICMP message. And second, that the packet ID matches our process ID. If either check fails, the loop continues waiting rather than giving up, which makes the application more robust. The TTL is extracted by unpacking the full IP header. The round trip time is calculated by reading the original timestamp we embedded into the payload and subtracting it from the current receive time, converts to milliseconds. Finally, the function returns all the results as a dictionary. Then we have the single ping function. The single ping function, it wraps the send and receive steps. It creates the raw socket here, and importantly, it catches a permission error and prints a clear message if the script isn't run as administrator, because the raw sockets, they require elevated privileges. The socket is always closed in the finally, blocking regardless of what happens, which is a good practice. Then we have the display function display result function. The display result function, it handles the output formatting. If the result is none, it prints the request timeout with the sequence number. Otherwise, it prints the bytes received, destination, IP, sequence number, TTL, and the round trip time to three decimal places, matching the format of the standard ping output. Then we have the main ping function, which is named as myping. The myping function is the entry point of the whole process. It resolves the host name first and exits cleanly if it can't be found. It then prints the required assignment line, ping destination IP addresses in Python, followed by the standard ping header line. It loops 4 times, calling single ping each iteration, tracking how many packets were sent and received, and calling the display result to print each line. There's a 1 second sleep between each ping, matching the real ping behavior. After the loop, it calculates and prints the summary: packets transmitted, received, and the percentage loss. If any replies were received, it also prints the minimum, average, and the maximum RTT values. Then there's an entry point. At the very bottom, the script asks the user to enter a hostname or an IP address when run directly. It strips any white space, checks the input isn't empty, and then calls my ping to start the process. Now let's switch to the terminal and show the application running. Run the Python file. Okay. So here I've opened the command prompt as administrator, and this is required for raw sockets. I'll enter the www.google.com. So it asked me for entering a host name or an IP, and I gave it a domain name which I want to ping. And I can see the required opening line prints first and then the ping header. Every reply shows the bytes received, the Google's IP address, the sequence number, the TTL, and the round trip time in the milliseconds to the 3 decimal places. The summary at the bottom confirms all the 4 packets were received with zero packet loss and shows the minimum, maximum, and the average RTT. Then again, we can run this and let's see if we can get a request timeout message. And here we can add any IP address. And here we can see that we got the request timeout for ICMP with the sequence numbers. So the summary correctly shows that 100% packet loss and no RTT statistics since no replies were received. This confirms the timeout handling works correctly. So that's the full custom ping application built entirely in Python using the raw sockets and the manual ICMP packet construction, handling both successful replies and the timeouts with accurate RTT calculation and proper summary statistics.